Hello everyone, my name is Trin, and today I will be discussing my selected one-way analysis of variance, which is called a one-way ANOVA, ANOVA. I will be explaining what this test is, when researchers can use it, how it is calculated, and when a post hoc test is needed. A one-way ANOVA is a parametric test that is used to compare the means of 3 or more independent groups. It is created through the work of a statistician. His name is Ronald Fisher during the early 20th century. ANOVA was important because it allowed researchers to compare several groups in one analysis. Conducting various multiple t-tests instead would increase the possibility of making a type 1 error, and that means concluding that a difference exists when it actually does not. The term one-way means the analysis has one categorical independent variable. It must also have one continuous dependent variable. For this example, I will be relating it to ophthalmology, the eyes. So, for instance, a researcher may want to compare 3 glaucoma medications to determine which treatment produces the greatest reduction in intraocular pressure. So glaucoma, for your information, glaucoma is a type of eye disease that could lead to blindness if it is not managed by specific treatments like eye drops, for instance, to lower down your intraocular. In this case, I will call intraocular pressure as IOP to shorten it. Intraocular IOP is the fluid pressure inside of your eye, reducing it is important to manage glaucoma. Participants could be randomly assigned to receive medication A, B, or C, so 3 different medications. The independent variable would be the type of glaucoma medication, whereas the dependent variable would be the change of IOP from the beginning to the end of the study. That will be measured in millimeters of mercury. The null hypothesis would state that there is no difference in the mean IOP reduction among the 3 medication groups. The alternative hypothesis would state that at least one group has a different mean reduction. A one-way ANOVA would be used in experimental, quasi-experimental, or observational studies. In this example, it would be an experimental study because participants are assigned to different treatment groups. Because ANOVA is a parametric test, there will be various of assumptions that will be needing evaluation. Firstly, the observation must be independent. Each participant should belong to only one medication group. That's very important. Second, the dependent variable should be approximately normally distributed within each group. Researchers can evaluate normality using histograms, Q and Q plots, or the Shapiro-Wilk test. Third, the groups should have approximately equal variances. This assumption is called homogeneity of variance and can be evaluated with Levene's test. A Levene's test result greater than 0.05 generally suggests that the assumption has not been violated. The main calculation behind ANOVA is fairly simple. It compares the variability between the groups from the variability within the groups. So for instance, the formula will be looking like F equals the top being mean square between groups, whereas the bottom is mean square within groups. The variability between groups represents differences that may be connected to the glaucoma medications. The variability within groups represents individual differences and random error. A larger F value suggests that the group means differ more than would be expected from random variation. Researchers usually compare the resulting p-value with a significance level of 0.05. If the p-value is less than 0.05, the researchers rejects the null hypothesis and summarizes that at least one medication of the group is significantly different. For example, this researcher might report a one-way ANOVA found a statistically significant difference in the mean IOP reduction among the 3 medication groups. F parentheses inside of the parenthesis will have a 2,87 close parenthesis equals 6.35, p equals 0.003. However, the ANOVA result only tells us the difference that a difference exists somewhere among the groups. It does not identify which groups are different, unfortunately. So that being said, a post hoc test is necessary in this case. Tukey's honestly significant difference test, or Tukey's HSD, compares every possible pair of groups' means while controlling the overall risk of a type 1 error. In this example, it would compare medication A with medication B, medication A with medication C, and medication B with medication C. Tukey's HSD is generally appropriate when the groups have similar variances and reasonably balanced sample sizes. If the groups have unequal variances, the Games Howell test may be appropriate for this scenario. Researchers, to perform this test in SPSS, select analyze, compare means, and one-way ANOVA. Place the change in IOP in the dependent list and place the medication group in the factor box under options. Select descriptive statistics and the homogeneity of various variance test. Under post hoc, select Tukey and then click OK. A meaningful result should include more than the p-value. Researchers should also document the group's means, standard deviations, F statistics, degrees of freedoms, confidence intervals, and an effective size such as ETA squared. The p-value indicates the result. The p-value indicates whether the result is statistically significant, while the effect size helps explain how large the difference is. In ophthalmology, researchers should also determine whether the reduction in IOP is clinically meaningful for patients. Overall, one-way ANOVA determines whether a significant difference exists among 3 or more independent groups. If the ANOVA is significant, Tukey's HSD identifies which group are different. Altogether, these tests can help assist ophthalmology researchers to compare glaucoma treatments and determine which medications would be more successful for patients. And that's all I have today. Thank you very much, and I hope that the video was meaningful and helpful. Thank you.